Okay, so now I'm going to show you guys how to use the epsilon-delta definition to prove that the limit is L. So using the epsilon-delta definition, which I will give you, to prove the limit is L, or whatever it is they give you. And L is just a variable, and I'll explain what this means in the next sentence that I'm going to say. So the definition of a limit is basically defined as, it's a definition, and this part is extremely important because this is what you're going to base your proof when you prove that the limit is L when it is given. So the definition of a limit is, as x approaches c of f of x, the limit is L. Which means that for each epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus c, which is less than delta, then f of x minus the limit is less than epsilon. So, like I said, this definition is given to you in the book. It is extremely important, especially when a question is asking you to use this definition to prove the limit is L. This is what they're asking you to base your proof on, especially these two equations here, and proving that such that for epsilon is greater than 0, there exists a delta greater than 0. This is really important to remember. Now, I'm going to go through an example with you so it kind of makes more sense and you can kind of see how exactly you're going to use these two equations, relate them, and use them to prove that the limit is L. Okay. So let's say that there's a question and it says, given a limit as x approaches negative 4, of the function 1/2 x minus 1, the limit is negative 3. Use the epsilon delta definition to prove that the limit is L. In this case, L equals negative 3, that's a limit. C equals negative 4. And f of x equals 1/2 x minus 1. Now these are all things that I just used my basic definition of a limit and I just kind of jotted these little notes down. I would highly suggest this. It makes it easier when you're going to plug these values back in to your epsilon delta definition. Now plugging these values back into your epsilon delta definition, you have 0 is less than x plus 4, which is less than delta, and you have 1/2 x minus 1 plus 3 is less than epsilon. Now, in order to prove this, in order to prove that the limit is negative 3 or the limit is L, you must show that for each epsilon greater than 0, there exists a delta greater than 0 such that this is less than epsilon whenever 0 is less than x plus 4 is less than delta. Okay, and so your goal is to relate these two equations and find a connection between the two. Okay, because you're trying to prove that epsilon is greater than 0 and so is delta. Okay, so for every epsilon greater than 0, there exists a delta greater than 0 such that 1/2 x minus 1 plus 3 is less than epsilon and 0 is less than x plus 4 is less than delta. Now, in order to relate these two equations, you're going to look at this one first, okay? And it's easier if you take this equation and try and relate it back to this somehow. So first we're going to simplify this to, so we have 1/2 x minus 1 plus 3 is less than epsilon. So let me just simplify this here so you can get 1/2 x, we can do 1/2 x plus 2. And just trying to relate it back to this, what we can do is we can take out a 1/2. So this is the same thing as saying 1/2 times x plus 4. So what we're saying here is that delta, which is greater than x plus 4, equals 2 epsilon, because x plus 4 here, 1/2 times x plus 4 equals epsilon. So x plus 4 equals 2 epsilon. So delta equals 2 epsilon. Having said that, putting this all together again, what's going to happen is you're going to get 0 is less than x plus 4, which is less than delta, which as we just discovered is equal to 2 epsilon. Okay, now this implies that 1/2 x minus 1, which was your function, plus 3, which was your minus your limit, equals, like we had said, 1/2 times x plus 4 is less than 1/2 times 2 epsilon, which is equal to epsilon. So you have just proven that epsilon is greater than 0, which therefore proves that the limit does exist.